Hi everyone, my name is Lavender and I am a senior at Carnegie Mellon. I'm here today to talk about edge entropy, which is a way to evaluate the difficulty of no classification problems. This is a joint work with my collaborator Zhang Xi, Mark Chan, Oren Wright, and Professor Jose Mora. So I will start by defining what a no classification problem is, and it has to do with this graph on the right here. Then I will formulate our research problem. After that, I will talk about our solution, which is edge entropy. And then I will support edge entropy with both results from simulated and real data sets. Finally, I will talk about our conclusion. So the task of node classification is to assign labels to each node given a graph G and the data defined at each node X, and also some but not all of the labels. So for example, on the right, you could see a citation network. Here, the nodes represent papers and the edges represent citations between papers. And you can see only a few of the nodes are colored here. And the colors represent category of paper. For example, the blue nodes could be a math paper and the green nodes could be a biology paper. And the data defined on each node is a bag of words. So our goal here is, given this graph with just a few color nodes, we want to make it into a graph with all color nodes. And we do that by predicting the labels of the remaining uncolored nodes. Now, one way to solve the node classification problem is using a graph neural network. And in this presentation, I will focus on the variant called graph CNN. Here, you see the architecture of a graph CNN. We give it two pieces of information. One, the adjacency matrix A. And the second one is the data defined on each node X. So given these two pieces of information, we would perform graph convolution. And graph convolution is just defined as P of A times X. And intuitively, what graph convolution is doing is it's aggregating the information from neighbors that are different hops away. And as you can see from the definition of graph convolution, what A is really will affect what graph convolution does. And as one could expect, if we fix the graph signal X and change the graph structure A, then the performance of this model will be different because we are given a different graph structure. And indeed, this figure shows the test accuracy of a graph CNN on Quora ML dataset, which is a citation network. So we train it with three different types of graph. We train it with the original adjacency matrix, or we ignore the graph structure and train with identity matrix. We also train it with a random Erdos-Renyi graph. Now, you see that when we train with the original matrix, the accuracy is around 80%. However, if we ignore the graph structure or use random graph, the performance is around 20% worse. And this makes sense because if we use identity matrix, then P of AX is just a scale version of the original X, which is not doing much. And if we use a random graph, then P of AX is aggregating the information of random nodes. And that's not adding a lot of information here. So then our research question motivated by this figure is that given a no classification data set, how can we evaluate its difficulty without training and testing? For example, in this graph, we see the Quora ML dataset with the original adjacency matrix is a relatively easy no classification problem, whereas the Quora ML dataset with the identity matrix or the random Erdos-Renyi graph is a relatively difficult no classification problem. So to answer this question, our intuition here is that if a node is connected to other nodes of the same class, then P of AX will average the data of nodes of the same class. And thus, it will make it easier to classify. So our solution to the research problem we formulated is based on this intuition, and we call it edge entropy. I'm going to formally define it here. And we say a null classification problem is relatively difficult if the edge entropy of its graph structure is relatively high. And to formally define edge entropy, we start with defining PLM, which is the probability that an edge in G that starts with a class L nodes will end at the class M nodes. So as you can see, PLM is a ratio of the cardinality of two sets. And the set at the top is the set of edges that start with a node of class L and ends with a node of class M. The set at the bottom is the set of edges that start with a node of class L. So then the definition of edge entropy for class L is similar to our old definition of edge entropy. The only difference here is we substitute E in PLM as the probability distribution. And we sum over all classes from 1 to n, where big N is the number of classes. And we use log of base big N because we want this per class edge entropy to be normalized between 0 and 1. And we could also define the average edge entropy to get a graph level idea. So the average edge entropy is a weighted sum of per class edge entropy. Here, Wm is the percentage of class M nodes. So because Wm is between 0 and 1 and Hm is between 0 and 1, our average edge entropy will also be normalized to between 0 and 1. To understand edge entropy a bit better, let's look at some examples. So again, we say a graph structure is effective if its edge entropy is close to 0. Let's first look at this bipartite graph. The blue nodes always connect with red nodes, and red nodes always connect with blue nodes. So in this case, the edge entropy is 0, and the graph structure is effective. For the graph in the middle, the blue nodes always connect with blue nodes, and the red nodes always connect with red nodes. In this case, the edge entropy is again 0 because the probability, because P blue blue is 1 and P blue red is 0. So the graph structure is effective. Now, for the graph at the very right, so you can see there are 3 edges that goes from a red node to a blue node, and 3 edges that goes from a red node to red nodes. So the edges here are not telling us much about the labels of its source nodes or end nodes, and the connection is quite random. So in this case, our edge entropy is 1, and the graph structure is not very effective. So now that we have some intuition about edge entropy, let's look at the relation between edge entropy and the test accuracy of some simulated data sets. So we generate our simulated data sets as Erdos-Renyi graph. We fix our parameters. So we would generate a graph of 3,000 nodes with 3 classes where there are 1,000 classes for each, 1,000 nodes for each class. And we manually fix 2 class-to-class connection probability matrix, P low and P high, such that the graph generated with P low will have a low edge entropy, and the graph generated with P high will have a high edge entropy. And then we run 100 Monte Carlo trials, and we also pick our Erdos-Renyi probability of an edge from 0.1 and 0.5. On the right, you could see an example of our generated graph. So there are 3 classes, as you can see the 3 clusters here. So the idea is we fix all other parameters while varying the edge entropy. And we see how the graph convolutional neural networks performance change as we change our edge entropy. Let's look at the result. So the left graph here shows the performance with p equals 0.1. So it's a relatively sparse graph compared to p equals 0.5. And the blue line is the performance when we train with a low edge entropy around 0.5. And the orange line is the test accuracy when we train with a high edge entropy around 0.97. So you can see the blue line is always above the orange line. And at 30% training data, the gap is around 20%. Now, for denser graph, this trend also exists. The blue line is always above the orange line, and with 30% training data, the gap is around 20%. So together, these two graphs shows that for simulated data sets with different sparsity, if we have a low edge entropy, then this data set is relatively easy. And if we have a high edge entropy, this data set is relatively difficult. We also tested edge entropy on many popular benchmark datasets. So this is the result for citation networks, Quora, Scicere, and PubMed. The blue line is the test accuracy when we train with the original graph structure, and the orange line is the test accuracy when we ignore the graph structure or when we train with the identity matrix. So you can see the gap again exists here. And let's look at its edge entropy. One thing worth noting here is Quora ML has the lowest first order edge entropy, and correspondingly, it has the highest improvement. And this meets our expectation because having the lowest edge entropy means it's relatively easy, so we would expect a high improvement. And on the other hand, PubMed has the highest edge entropy and correspondingly the lowest improvement. This again meets our expectation because a high edge entropy means a more difficult node classification problem. We also test edge entropy on the citation networks and a social network called Reddit using a two-layer graph attention networks. Again, here, Reddit has the lowest first-order edge entropy and correspondingly the highest improvement. We also test edge entropy on two large simulated datasets called SBM cluster and SBM pattern. Here, SBM pattern has a lower edge entropy and correspondingly a higher improvement. So again, this meets our expectation because having a low edge entropy means the node classification problem is relatively simple and we will expect a higher improvement. So in this presentation, we show it's challenging to evaluate the difficulty of a node classification problem just by looking at the graph. And our solution to this problem is edge entropy. We say a node classification problem is relatively difficult if its edge entropy is relatively high, and we say it's relatively easy if its edge entropy is relatively low. And we saw the usefulness of edge entropy through evidence from both simulated and real datasets. For future work, we are looking into higher order edge entropies. So that's the end of my presentation. Please feel free to leave me any questions.